In the 1600s, Sir Isaac Newton formulated the laws of motion and universal gravitation. Ideas that revolutionized how humans understand the universe. But with it came a dirty little secret. While Newton could explain the relationship between the sun and the earth, and the relationship between the earth and the moon, he couldn't explain the relationship between the sun, the earth, and the moon. Two bodies, like the sun and the earth, or the earth and the moon, follow Newton's laws of motion and universal gravitation to form stable, predictable trajectories. But for some mysterious reason, three bodies, like the sun, earth, and moon, do not. So their trajectories are unstable and unpredictable. Today, we call this problem the three-body problem. For hundreds of years, the greatest minds have attempted to solve this problem, without success. Although no generalized, analytical solution exists for the three-body problem, we can use computers to generate numerical solutions that closely approximate a general solution. How can we use the DifferentialEquations.jl package to solve the legendary three-body problem in Julia? Well, let's find out. Welcome to Doco.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 10 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the DifferentialEquations.jl package in order to solve first-order ordinary differential equations, second-order ordinary differential equations, and systems of differential equations. With that said, let's get started. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it Three-Body Problem. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Just for reference, I'm going to add a link to the Wikipedia article on the three-body problem. Next, let's add a few packages. Now that everything's loaded, let's describe the problem that we're trying to solve. So here's the setup to the three-body problem. There are three bodies in space with mass m1, m2, and m3. Their initial positions are given by the vectors r1, r2, and r3. If you're in two-dimensional space, then the position vectors have two elements for x and y. If you're in three-dimensional space, then the position vectors have three elements for x, y, and z. In order to simplify the calculations for this tutorial, I'm going to use two dimensions. At time 0, each of the masses has some initial velocity, which is known. So, given the masses, their initial positions, and their initial velocities, calculate the positions of each of the three bodies at any time t. Sounds simple enough, right? So here are the equations that we need to solve. These equations are a little confusing because they combine differential equations with linear algebra. In these equations, R1, R2, and R3 are the position vectors for the three bodies. The double dots that you see is shorthand for second derivative with respect to time. A single dot would mean a first derivative with respect to time. You'll recall from the projectile motion tutorial that the first derivative of position is velocity, and the second derivative of position is acceleration. So what you're looking at is a system of second-order ordinary differential equations that define the acceleration of the three bodies with respect to time. So the first equation shows how the first body, with mass m1, is impacted by the gravity of the second body and the third body. And the second equation shows how the second body, with mass m2, is impacted by the gravity of the third body and the first body. And the third equation shows how the third body, with mass m3, is impacted by the gravity of the first body and the second body. These are the famous unsolved differential equations that make up the three-body problem. So the equations are known, but the analytical solution to them is not. The other confusing bit with these equations are the vertical bars. Those vertical bars do not stand for absolute value. The vertical bars indicate the norm, or the length, of a vector. So for example, that R1 minus R2 in between vertical bars means the distance between body 1 and body 2. G is the gravitational constant, which has this value. Using this value will make it difficult to find a numerical solution. So for simplicity, I'm going to set the value of G to 1. This will simplify our calculations and will allow us to plot the numerical solution. But as a result, our solution will be abstract and dimensionless. At first glance, this doesn't look too bad, right? The three-body problem appears to be a system of differential equations with three equations, just like the Lorentz system. But these are second-order differential equations. I couldn't figure out how to solve a system of second-order differential equations using the DifferentialEquations.jl package. But the standard way of solving a system of second-order differential equations is to create a system of first-order differential equations that includes both the first-order and second-order differential equations. That means these three equations will become 6 equations. 3 for the first-order equations, and 3 for the second-order equations. And if that wasn't enough, there's another complication. We need to solve both the first-order and second-order equations for each position element of the three bodies. Since the position of each body is defined by an x and a y coordinate, that means we have 6 position elements, 2 for each of the three bodies. 6 position elements plus 6 differential equations means 12 differential equations in total. If you're trying to solve the three-body problem in 3 dimensions, then you need to add 6 more equations for a total of 18 differential equations. Now that's a lot of equations. The most that we've seen so far in a system of differential equations is 4 equations, for the double pendulum problem. So we have a lot of work ahead of us, but trust me, it'll be worth it. I know this is lame, but in order to save some time, I'm going to do some copying and pasting. There's a lot going on in this LaTeX, so for those of you who are interested, you may want to spend some time going through this code at your convenience. There's a link to my code in the description below. Here are some clarifying remarks from the Wikipedia article. For the DifferentialEquations.jl package, we need to set up a Julia function that takes the arguments du, u, p, and t. This function will contain a system with 12 equations. In this LaTeX, I'm using the prime notation to indicate a first derivative with respect to time. There's a lot going on in this Julia function, so let's take some time going through it. Just like examples that we've seen before, we start by defining the unknown functions. The biggest difference here is that we have 12 of them in this function. Next, we need to define the parameters for the masses of the three bodies. Next, we need to set up the first derivative of the positions with respect to time, which will give us the velocities in the x and y directions for each body. Before we set up the second derivatives, let's perform some intermediate calculations for the distance between the bodies indicated by the vertical bars in the LaTeX equations. This is just the Pythagorean theorem in action. Finally, we can set up the second derivatives. All I did was convert the LaTeX equations into Julia code, and then split each equation into the x and y elements. I left off g since I'm setting the value of g to 1. This is a really long function, so I'm guessing you won't be able to read it on the screen, but here's a look at the entire function. Okay, now that we have our Julia function, let's set up the variables. We have 12 variables to assign for u. Let's start with the initial positions of the three bodies. I'm going to set up some widgets so we can change these values later. There are 6 widgets to set up, but you can copy and paste this code and just make a few minor adjustments. For simplicity, I'm going to set up the initial positions of the three bodies at the vertices of an equilateral triangle. Next, we need to set up the initial velocities. Again, for simplicity, I'm going to give each body the same initial velocity, but in different directions. the initial velocity is a vector that is tangent to the invisible circle that is circumscribing the equilateral triangle formed by the three bodies. Now that we have the initial condition set up, we need to place all 12 variables inside of a vector. For the parameters, there are only 3 for the masses of the three bodies. Again, for simplicity, I'm giving all three bodies the same mass. Now that we've set up the parameters, we need to place the variables inside of a vector. Okay, now the only thing left is our standard setup for time. I say standard setup, but for today, I'm using an increment of 0.001 units, which is a smaller time increment than we've used in the past. Okay, we are now ready to define our problem. After all of that work, you'll be happy to know that we can simply use our trusty ODE problem function. Now that we've defined the problem, we are now ready to solve it. In order to solve the three-body problem, all we need to do is use the solve function. I'm going to use the Vern7 solver again, but this time I'm going to set the relative tolerance and the absolute tolerance at 1 times 10 to the negative 16th power. And that's it. It's so simple that even a doggo can do it. I'm not sure what Newton was complaining about. I'm just kidding. This is a numerical solution, which is an approximation of an analytical solution to the three-body problem that doesn't exist. But it's still fascinating, so let's take a look at the solution. There are 12 columns of values. The first 6 columns are the positions, and the last 6 columns are the velocities. The value 1 column contains the values for x1, which are the x-coordinates for the first body. The value 2 column contains the values for y1, which are the y-coordinates for the first body. Similarly, the value 3 column and the value 4 column contain the values for x2, y2, which are the coordinates for the second body. And the value 5 column and the value 6 column contain the values for x3, y3, which are the coordinates for the third body. The value 7 column contains the values for vx1, which are the velocities for the first body in the x direction. The value 8 column contains the values for vy1, which are the velocities of the first body in the y direction. Similarly, the value 9 column and the value 10 column contain the values for vx2 and vy2, which are the velocities for the second body. And the value 11 column and the value 12 column contain the values for vx3 and vy3, which are the velocities for the third body. For the most part, we'll be focusing our attention on the first 6 columns, which contain the position values for the three bodies. Because these values are contained in a vector of vectors in the solution, we need to do a little prep work before we can plot the positions. I modified the code that we used in the last tutorial to extract the values from the solution. I know it looks like there's a lot going on in this function, but that's only because there are 6 columns of values to extract. All this function is really doing is pulling the x values and the y values for the 3 bodies from the solution, and then placing the values into separate column vectors, so we can use them for plotting. Now, we can use this function to extract all of the x values and all of the y values. Let's also set up some variables to keep track of the x and y positions for each of the 3 bodies at any time t. Okay, we are now ready to generate some plots. Let's start by plotting the solution to see what it looks like. So, this is an interesting plot. It's kind of a mess. Is this what you were expecting? This plot contains all of the x positions and the y positions, as well as all of the x velocities and the y velocities for all 3 bodies from time 0 through time 100. Even though this looks interesting, we're not going to spend any time on this plot, since, believe it or not, we have even more fascinating plots to look at. Let's suppress this plot and move on. Just for fun, let's use the Julie logo colors for the 3 bodies. Conveniently, we have all of the x values and y values contained in variables appropriately named x_values and y_values. This plot is kind of a mess too. Is this what you were expecting? Let's suppress this plot as well, so we can add some dots to represent the 3 bodies. So in this plot, the red dot is body 1, the purple dot is body 2, and the green dot is body 3. The curves show the trajectories of the 3 bodies in their respective colors, from time 0 through time 100. As you can see, the trajectories are a mess, with multiple loops everywhere. This is nothing like how the Sun, Earth, and Moon behave. Or is it? It would be really helpful to see the bodies in motion, so we can see how the positions of the 3 bodies change over time. Let's set up our control panel by pulling down the widgets so we can perform some analysis. Now let's pull down our plot and then hide some of this code. Let's start by moving the time slider to 0. So these are the initial positions of the 3 bodies. The red dot is body 1, the purple dot is body 2, and the green dot is body 3. The 3 bodies are starting at the vertices of an equilateral triangle. and they have the same initial velocities, moving in a clockwise direction that is tangent to the invisible circle that circumscribes the triangle. As we move forward in time, the three bodies are all attracted to one another. These bodies are point masses, so there's no collision built into this model. If a body comes close to another body, they're just going to pass through each other in this model. Even though all three bodies started at the same initial condition relative to one another, it doesn't take long for that symmetry to fall apart. As you've probably figured out by now, the three-body problem is yet another example of a dynamical system that's chaotic. But how can that be? The Sun, Earth, and Moon don't behave chaotically. Or do they? It turns out that they do. The reason why we don't perceive it is because the time horizon for humans is so small relative to the time horizon for the universe. Chaotic behavior of the universe can be observed when simulating its motion over millions or billions of years. And just like the Lorentz system and the double pendulum, the three-body problem is highly sensitive to the initial conditions. Let's change some of these settings to see what happens. All I did was make a minor change to the initial value of x1, which is the initial x-coordinate of the first body. As you can see, this is a completely different trajectory. In a three-body system, it's common to see two of the bodies form a binary pair, while the third body is ejected from the system. So in this example, you can see that the red body and the purple body have formed a binary pair, while the green body has been ejected from the system. This is something that you'll see over and over again as we change the values of the settings. You see, in this scenario, the red body and the purple body have formed a binary pair, while the green body has been ejected from the system. But it looks like the green body is trying to rejoin the party here. In this case, the red body and the green body have formed a binary pair, while the purple body has been ejected. Same thing. The red body and the green body have formed a binary pair, while the purple body has been ejected. In this case, the purple body and the green body have formed a binary pair, while the red body has been ejected. This time, the red body and the purple body have formed a binary pair, while the green body has been ejected. So unlike the Lorentz system and the double pendulum, the three-body problem is not confined to a finite space. In fact, it's common for a body to be ejected from the system, which is why the three-body problem is used to calculate how to hurl satellites into interstellar space. Let's try changing the initial velocities to see what happens. So this one's interesting. In this scenario, none of the bodies have been ejected yet. We can observe similar behaviors when we change the values of the masses. Fascinating, right? This really makes you think. So, is the three-body problem what you were expecting? For me, this is not what I was expecting. I was hoping to generate some sweeping orbits that I could set to symphonic music. But when you consider that these bodies could be stars or planets, many of these trajectories are downright terrifying. We like to think that our solar system is a stable system that's been around for billions of years, and will be around for billions of years more. But how stable is it really? The numerical solutions to the three-body problem demonstrate that a three-body system exhibits chaotic behavior that is highly sensitive to the initial conditions. Since we don't know the initial conditions of our solar system, and will never know, how can anyone make an accurate long-range forecast about the fate of our corner of the universe? Fortunately, when it comes to our solar system, a long-range forecast means billions of years into the future. So I'm guessing we should be okay until the next tutorial. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.